Okay, here goes part two. We look at specific heat. So first of all, in the previous video lesson we talked about the jiggling of molecules being what heat actually is. So when we talk about temperature, it's actually a measure of the average kinetic energy of the particles in an object. Whereas total thermal energy, so we might call this total thermal energy, is the total kinetic energy of particles in an object. So the difference between average and total is this. So we could have a hot, say this is water in here. So you have a little cup of hot water and you have a big bowl of warm water. So the temperature of this is obviously greater than this because it's hot and this is only warm. But the total thermal energy could be equal between these two. So there are fewer molecules in here, but they're moving faster and so have more kinetic energy. And there are more molecules, but each of them has less kinetic energy. But in theory, we could have the same total thermal energy. This one is obviously greater temp, so yeah, more temperature, and this would be less temperature. Okay. Thermal equilibrium is, or describes a situation when two objects or an object and its surroundings are at the same temperature. So let's see. Rate of energy flow between two objects is equal. So imagine that okay, fine. If you were to stand outside and it's cold outside and you were to stand there forever, let's say it's 20 degrees outside, eventually you would freeze and die and your body would be 20 degrees. So you would be in thermal equilibrium with your surroundings. I don't recommend it. But the rate of energy flow between two objects is equal, so there would no longer be heat energy being transferred between your body and the outside surroundings. So if right now, here you are, you were to go stand outside and it's 20 degrees outside, heat would flow out of your body into the atmosphere or your surroundings because you are at a higher temperature. The heat energy will always flow from the higher to the lower temperature object. So let's see, here's an example. You heat up a cup of water in microwave and place it outside when it's cold. Okay, so this is kind of just what we talked about. You got a cup of water, and the microwave is going to increase the temperature, which I'm going to represent just like that. Okay, so it's kind of, a microwave, that's sort of a different procedure, but it's like heat going into it. And then if we were to take that and put it outside, where it's nice and cold, the heat would flow out of the cup of water. So in the above example, how did the heat energy leave the water? All right. So we have these are different ways in which heat energy can be transferred. We have conduction, convection, and radiation. So here's an example for each. Conduction is if you lay down in the snow. If you lay down in the snow, it's obviously very cold, and that feels colder than simply standing. So you could sometime try standing outside naked, make sure it's night so no one sees you. Stand outside naked and it's winter and it's cold, and it's going to be really cold. But if you're to lay down in the snow, it actually feels colder, and that's because the heat is being conducted away from you. So a definition would be if two objects are in contact with one another. So your body is in contact with the snow, and the heat would transfer from your body into the snow at a greater rate than if it were not in contact with the snow. Convection has to do with the fact that air molecules can transfer heat. So the example of this would be you stand outside on a winter night. And you can still do this wearing clothing, and you'll still get cold, and heat will still be pulled away from your body using convection, but the clothes are obviously good insulators. So convection is air molecules transfer heat. And then radiation, this isn't like a dangerous, harmful medical radiation like radioactive decay, plutonium or whatnot. An example of radiation would be the sun. So if you stand outside in the sun, it heats you up, but there's nothing actually touching you, right? It's not air molecules from the sun that move from the sun to your body to heat you up. If you stand outside in the sun, it's basically electromagnetic waves, which we will talk more about later, but they are transferring heat energy. So transfer heat energy. And standing in front of a fireplace is the same. If you have the fan on behind the fireplace, that would be convection because it's moving air molecules, hot air molecules over to you. But just the hot objects will radiate out heat. So electromagnetic waves, we'll learn more about that in the future. And okay, so specific heat, I think you've heard about this in the past, but here we go. It's a measure of how much energy is required to raise 1 kilogram of a substance by 1 degree Kelvin. And in chemistry, you probably heard about it in terms of degrees Celsius and grams, but this is what we use in physics. So for water, we have 4,180. The specific heat of water is very large, meaning it takes a lot of energy to raise a certain amount of water at a certain temperature. Copper, being a good heat conductor, if you have copper bond pans in the kitchen, those tend to be, one, expensive, but two, good for cooking because they transfer the heat quickly. Notice how it has a low specific heat, meaning it doesn't take a lot of energy to raise some copper by some temperature, and then aluminum is somewhere in the middle. Here's our formula. Q, heat energy, and this is measured in joules, and here we have mass of substance that is being heated or cooled. C is the variable we use for specific heat. Specific heat, and delta T is change in temperature. Change in temperature. Okay, so that's what the formula looks like. Let us work through an example. If you want to heat up a cup of water, 500 grams, so this is the amount, that's half a kilogram, from room temp, 25 degrees Celsius to boiling, and boiling we know is 100 degrees Celsius, how much heat energy is required? So, heat energy, MC delta T. So, how much heat energy, Q, this is what we're looking for,